Hello there. Welcome to a presentation which I've entitled Looking Closely at the Quadratic Function y is equal to a in brackets x minus h squared plus k. This is something we're familiar with, and we've done this at school using plotted this kind of function using table of values. The aim of this presentation is to sort of highlight the main characteristic of the function, especially this graph, so that can make it easier to plot it without tedious use of a table of values. So we look at this function as follows. Note that the simplest version of this function is when a is equals to 1, h equals to 0, and k equals to 0. In that case, we can all see that what we get is x squared. That is, if you substitute here a equals to 1, h is this, we're only left with x squared here plus 0, which is x squared, which was simply going to call our standard quadratic function. We know that we plotted this at school using the table of values, which looks as follows. We'll get here, for example, we'll take just 4 values from -2, -1, 0, 1, and 2. And we square these values, like square 0, square 1, get 1, square -1, get that, and -2 gives you 4, and 2 also gives you 4. And we plot a graph which is like this. And what is important here is that to highlight that we are actually looking at a standard graph where a is equals to 1. In that case here, a squared, 1 squared will give you 1 squared, and equally -1 squared will give you -1 squared. Then you get a graph which is like this, and you can see that this graph is a symmetric graph, like we can see on the table of values here. A 1 here can be looked as a mirror image of 1. 4 also can be looked as a mirror image 1, as long as we put our mirror along x equal to 0. In that sense, we're simply saying that the line, the vertical line x equals to 0 is a line of symmetry for this graph. So now what we're going to do now, in this general graph here, which is y equals to a x minus h all squared plus k, we've actually isolated, we want to isolate the value a and see what is influenced in the graph, and this by setting h equals to 0 and k equal to 0, whereby the equation simply remains as y is equal to ax squared, which in this case, if a is equal to 1, we get this kind of a graph. Now what we want to do, we want to change now the value for a, which is 1, to another value. In this case, let's start with the a greater than 1. This is what we would see. In this case, we have chosen here that a be equals to 2. That's what a is there. And here, this is the standard graph. We've got a equals to 1. Now we'll take an example of a value like 1 and a -1. In this case, if we take this function and let's say it's f of x equals to 2x squared, then you evaluate it at 1, you see that we're going to give 2 times 1 squared, which is going to give you 2. So you see that in the standard function where the value was 1 at this level, it is now going up there. Similarly, if we go to -1 here, and we say f at -1, and we then get 2 multiplied by -1 squared, which is equals to 2. So I wrote 0 here, this is supposed to be 2, and then what you get here, you get again the value here at 2. Note that here the value of f at 1 and f -1 equals to 2 is also giving us that sense of the graph being symmetric, meaning that at points like this, which are symmetric around the y-axis, we get this the values is the same there. Actually, these 2 points being the mirror image of each other, and they're actually at equal distance from the line of symmetry, which is in this case is still the line of symmetry is x equals to 0. So that's what we get there. But summarizing what you see here, since we look at a is equal to 2, we must notice that 2 is greater than 1. You can see actually that the graph actual grows up fast. Like at 1 it was 1 in the standard, but now at 1 is 2. So then the graph rises and then narrows along around the line of symmetry. Now looking at the next case now, where actually a is less than 1, we get the following. We have got here the standard graph giving us that point here 1 1 on the graph. But now if we do this, if we take this function f at x equals to half x squared, in this case you see here that our a is equals to half, and that is less than 1. And then you see that at 1 now, this point, the point on the graph will be 1 comma half, which means now the graph actually is lower, which means then this coefficient a half slows down the growth of the function, else where it was supposed to be 1 now is half. And what we see about the graph is that the graph widens and it becomes wider than the standard graph. So if we even take this coefficient is smaller than half, you'll get the graph widening more around the y-axis. So that's what we have seen there. So coming back to the standard graph with a greater than 1, we've got to see what we observe in the graph is that this graph is facing up, which you could describe as cup up, meaning is a cup facing up. Now on the other hand, now just imagine what would happen now if we take a less than 0. Now if we're taking a equals to 1 greater than 0. Now we could take a equals to minus 1 in this case, which is less than 0. So what we're going to get is the following. So the standard graph will still continue going cup up that way. But now if we evaluate the standard graph here and then multiply it by negative 1, obviously this 1 which is here multiplied by negative 1 will give us a minus 1 this side. So which in this case the graph will part from here going downwards and then giving us another shape here which we could call cup down. That is important to understand then the effect of a on this graph, the narrowing around the y-axis, the widening, and then changing to negative a's, flipping the graph upside down. That is important. So that can be summarized in this kind of a table. Like there is the standard graph, there is the standard representation of the quadratic function, which is this way, which we know also can write in this form. And then we can see here that we've got 3 graphs here. Obviously this one, if it's a standard a here, will be equals to 1, and there a will be greater than 1, and for the red one a will be less than 1, and all these a's here are all a's greater than 0, and then all the curves here, they are graph up. And because we're still considering h and k equal to 0, so the line of symmetry remains being x equals to 0, which is actually our h. Then moving forward now, we would like to see what's the effect of h, and let us see what's the effect of k. So now notice that if we take this graph and set a equals to 1, h equal to 0, and k equal to 0, this graph this expression actually we can write it as x minus 0 squared plus 0 for k, which actually reduces to x squared, which is our standard graph. And you can see there x equals to h is the line of symmetry. In this case, when the graph is like this, is x equal to 0, which is actually the y-axis. And also what we see here is that this graph from the left is decreasing, and from 0 here it starts increasing. So then we call this point here the turning point of the parabola. and as you can see, its coordinates are 0, 0, which actually coincide with the values of h and k, so it's hk. So always going to say that the hk in that equation, the general equation, y equals to a x minus h squared plus k. These numbers h and k represent the turning point. That is standard. Now moving on, we have the following. Let's set again a here b equals to 1, h equals to in this case now h equals to 0, and then k equal to 0. That is for the standard graph. Now if we take a graph of this nature, like for example where h is not equal to 0, we can take this as follows. That's for example, we can take an example which says y is equals to x minus 2 all squared, and we want to compare this with the standard graph, which will be x minus 0 all squared, which we can simply write as x squared. Now if we look at the standard curve, we already said here the line of symmetry is x equals to h. So in this case here, our h is 0, so which means our line of symmetry is x equals to 0. Now at this point, we need to reflect that the function here is actually a square function. The function squares, and then if it squares x, then we're going to say now x here is actually the argument of the function. So in this case, what you are being told here, we're being told that this square function has a line of symmetry when its argument is equal to 0. Now this function, as a modified function of this one, would also say this function would have its line of symmetry when its argument, the square function, when its argument is equal to 0. That would take us to saying x minus 2 equals to 0, and then this equation takes us to saying x is equals to 2. So which means now if you compare this standard function and that one, you will see that the line of symmetry would have moved from 0 to x equals to 2. So then that's what is being shown here, that if we've got the equation of the graph written this way, h, which is here, actually gives you where the line of symmetry is. But also we know that the line of symmetry, where the line of symmetry is actually also where there's a turning point. Now if we were to calculate the k coordinate here, we'll be basically calculating the value of y. So in this case here, we would say exactly when x is equal to 2, y will be equal to 2 minus 2 all squared plus 0. So then what would happen there? Now we'll get 0 here, then it tells us that y is equal to 0 plus 0, which is 0. Now the turning point there would be then 2 comma 0, which is actually confirming again that our k in this case will be equals to 0, since h comma k will be the turning point. So in this graph here, this one, the turning point will be simple at 2 comma 0. So in this case, when the graph has been translated this way and our k is 0, our turning point will be simple h comma 0. In this case, considering any h different from 0. So what has happened actually when it's like this and our 2 here, you can see the 2 here is positive. The graph has been shifted from here to the right, and we call that the horizontal shift to the right. That is the motivation for using our h there. So in a different case, let's look at the following now, at the influence of k. Now in this graph, we're comparing the standard graph, which is we can actually write here as simple x squared, a equal to 1, h equal to 0, and that. But in this graph now, we consider now the condition where a is equal to 1, h is different from 0, and the k is different from 0. Now, we've already seen that if we write h here, that h will indicate a horizontal shift of the graph to the right. And then now, let's say we've got this kind of a function, x minus 2 squared plus, let's say, 1. Now, we've seen already that this h here will shift the graph horizontally to the right to 2. So in this case here, our h will be 2. And then, now knowing that h comma k is the turning point, now to calculate the value of k now, would simply now substitute this x by h, we then write y equals to 2 minus 2 all squared plus 1. Then we get here 0 and 1. Then our y becomes 1. So our hk simply becomes 2 comma 1, which will be then the turning point of that function. So once now in this graph we see the evidence, the influence of both h and k simultaneously. In this, h will shift the graph line of symmetry horizontally to the right, and then k shift the graph vertically up one unit. In other words, plus 1 unit, 1 greater than 0. Then the graph goes up. That's what happens there. Then let's look at a different situation now. What we've seen here is shift to the right and a shift upwards. So let's look at a different situation. We've got the following. Let's say now still h is different from 0 and k is different from 0 and a is equal to 1. So we saw the first graph, what we got is this graph shifted to the right when h is greater than 0, and shifted upwards value of k greater than 0. Now if we look at this, if we now change then this k, let's suppose that this h is a negative number. So in this equation we'll simply write y equals to x minus, our h is a negative number, minus h. In this case we're considering this point here symmetrical to that, all squared plus our k. We see a k also in this case is going in the direction of negative, then we've got minus k there. Now simplifying here, you'll see that this graph generally will look like x plus 1 plus h all squared minus k, which you can actually simply write as plus k. It doesn't really make a difference, but when is minus k, it simply shows that the graph will go downwards, it will put downwards. So we may merely leave it as just minus k. But when you look at this in general this way, we must know that k can be positive or negative, and then the influence of that. So if you can see that, you see that the brown graph, which was standard graph here, is y equals to x squared. When you come to this kind of equation, the graph, because h is negative here, the graph has been translated or shifted to the left by h units to get to minus h, and then k, it has been shifted from 0 there downwards by minus k units to get to this, to get here the turning point being minus h comma minus k. So at that point now, when you look at the general equation there, now you understand the meaning of all the parameters. Like then, what we're going to have now is the following: all the influences of that. What we've seen now, we've seen what happens when a is greater than 1 and h is 0. We've also seen what happens if a is between 0 and 1. And we've also seen what happens if a is a negative number, then we get this Cupdown situation. So in general, when we look at the equation of the quadratic function like this, we need to be able to decode all the messages which are given to us by the parameters like a, h, and k. But you also know, we see that you were given a square here, which is actually a perfect square. We can expand it in this manner in using our binomial expansion, and distributing this a, we get an equation like this, which finally ends up looking like this. Now, if we compare with the other form of the ternary curve of this curve, which is a x squared plus bx plus c, we notice that b is equal to the coefficient of x here, and the c is equal to independent term, which gives us these two relations between b and a and h, which lends us to saying h is equal to minus b over 2a. This is something very important to know. So now, if we get the equation like this, this can give you an idea of how you can go back to this form, which easily give you a way of plotting the graph. And on the other hand, then you get c also being equals to this. But in this case, you see what will be unknown here. Like here, your unknown will be h, and here your unknown will be k. So making k such a formula, you get k equal to c minus a h squared. But already we have had h there, so which means it will be now easy to arrive at this equation using this equality. So I think at this point I've highlighted all the important characteristics of the parabola. Then what our next practice will be to try to get into detail of how we can summarize the process of getting to this form of equation, which is easy to plot. So otherwise, at this point, I would like to say thank you for listening. My name is Charles Sugasfani Msipa.